Okay, so welcome everyone. Today's lecture will continue where we left off yesterday. I will finish off some things that I had planned to do yesterday, but did not have time for. Mainly what is called killing fields and how they relate to symmetries of manifolds. And then we will move on to discuss what is called differential forms and to see how that can be used in defining integrational manifolds. So let's dive right in, and as usual, feel free to either write questions in chat or just interrupt me with any questions you might have. So symmetries. So we talked for 4 lectures about symmetries, right? But we can also imagine that a space, a manifold, might have some symmetries by itself. So you might think of a sphere. A sphere is rotationally symmetric, and we'll discuss now a little bit about what that means and how we can describe it. So let's discuss the symmetries of so-called Riemannian manifolds. And if you have not come across the word Riemannian manifold before, that's just a space which is equipped with a metric tensor. So there is some notion of an inner product on the tangent space. The typical example here we're going to look at is the sphere. So S2, because you're kind of familiar with what the sphere is and what the symmetries of a sphere should be. So if I draw a sphere like this, you can imagine that this is a space with well, the surface of a sphere. You can describe any point on the sphere. So let's take a point here. And if we embed the sphere in 3 dimensions, you could have your coordinate axis something like this. So these are the x, y, and z coordinates. The sphere here is the set of points such that x squared plus y squared plus z squared is some radius r squared. So I can describe any point here. For example, this point that I drew. If I draw the line to the origin, I can use the coordinates theta being the angle from the z-axis, and if I project this down to the xy plane, I have the angle phi, and I can use these 2 coordinates to describe the sphere. And if I do that, the sphere has a metric tensor, and that metric G is given by d theta tensor d theta plus sine squared theta d phi tensor d phi. So this is a 0-2 tensor. It takes 2 tangent vectors and it maps them to a number defining the inner product, right? Now you know that the sphere has a symmetry group, which is SO3. So we can do any kind of rotations here in 3 dimensions. The sphere will look the same. So if we just discuss here a little bit what such a rotation would look like. So consider a rotation around the z-axis. This would essentially send theta to theta. So we're rotating around the z-axis, so the angle to the z-axis, which was theta, remains the same. And we would send phi to phi plus s, with s being a continuous parameter. So that would be a rotation of the sphere around the z-axis by an angle S. So this means that if we have a fixed point that's given by theta 0, phi 0, that's going to map to theta 0, phi 0 plus S. So this is 1-to-1, and it's continuous in S. And we can write down the tangent vector. So for any given point, so if this is the point P, for any point P, we can write down the corresponding curve. So we would have, let me call it gamma of P, which is a function of S. That's just this given by this this transformation. So this point P maps to another point, which is this gamma P of S. So that's a curve, and as it is a curve, it's going to have a tangent vector. And that tangent vector, well, it's gamma dot P, and that's the, by definition, it's the has the components of the YA dt, or sorry, the S. S was our curve parameter now. So by definition, these are the components of that of that tangent vector. Yeah. So if we insert this expression here now, so the derivative with respect to, should be a 0 by the way. If we insert the expression here for the new coordinates, the theta coordinate is constant, so its derivative with respect to S is 0, so we have no component in the theta direction. And if we differentiate the phi component with respect to S, we just get 1. So this means that this gamma P dot is just equal to the basis vector d phi, because we have the component 1 in front and we have the component 0 in front of the theta. So this actually means that if we take the set of curves like this, they are the flow, they describe the flow of the vector field d phi. So the vector field, the flow of the vector field d phi defines this symmetry. If I just took d phi and I would use that flow, that would define the symmetry of the sphere. It would define this rotation, because I would have exactly the same mapping of points. And this is essentially what the killing field does. So a killing field is not that it kills anyone. It's a German surname from the German mathematician Wilhelm Killing. And what we do is the following, that we consider now a map F which goes from some space to itself. And we want to think about, what does it mean for this to be a symmetry? Well, we discussed this, as I said, we discussed it for 4 lectures already. It means that something does not change. And in this particular case, we say that F is a symmetry of this Riemannian manifold with a metric if the pullback or push forward, depending on how you do it, of G, the metric tensor, is the metric tensor itself. So nothing happens to the metric tensor when you use this mapping F. So this is how we define a symmetry. So in particular, if we look at the flow of any vector field K, so that was a map from the space to itself, right? And it depends on the parameter S, which is continuous, right? Then we know that what we defined here last time, that this mapping is a mapping from M to M. So this was the flow of K for some given curve parameter S. So this is a mapping from M to M. So this is a symmetry if what we just defined holds true, right? So if gamma sk star g is equal to g, then the flow of this vector field describes a symmetry. Okay, but what does that mean? If you think back to what we did yesterday, we defined the Lie derivative. Was one of the things we did. And the Lie derivative, we defined it as follows. We said that that if we take the Lie derivative in the k direction of the metric in this case, then that by definition was the limit when s goes to 0 of 1 divided by s, and then gamma sk star g minus g, right? So if the flow of this vector field defines a symmetry, then we know that this is equal to not 0 but to g itself, because nothing changed. And then we just take g minus g, which is 0. Hope I don't need to convince you of that, and we get a Lie derivative of 0. So if your field describes a symmetry, if the flow of the vector field is a symmetry, then the Lie derivative in the direction of the field of the metric is equal to 0. Those two are equivalent statements. So such a field is called the killing field. So a killing field defines a flow which is a symmetry of the space. So for example, this example with the sphere that we had, the killing field would be just the coordinate basis field phi. That defines rotations around the z-axis. You can have, of course, any rotation here around any axis is going to be a symmetry. Those killing fields are going to have a somewhat more complicated expression. It's not going to be so easy as to just take one of the coordinates. So this means that if we have a field, we can take this corresponding Lie derivative of the metric, and we can find out if that field defines a symmetry or not. So let's take that example just for 2 seconds. So the example d phi on the sphere, we can check that this actually satisfies this condition, right? So if we take the Lie derivative in the d phi direction of the metric, and then I need to show that this derivative in itself is a rank 2 tensor, so I need to check that all of the components are 0. So if I take the theta component here, for example, if you remember, we wrote down the expression for how the lead derivative acts on a rank 2 tensor field. This will be equal to d phi g theta theta plus g phi theta d theta acting on 1, and this 1 here is the vector component of d phi, so it's the 1 that's in front here, plus g theta phi d theta 1. And as you are aware, if you differentiate 1, you get 0. And if we look at the metric tensor that we had here, the theta component of this metric tensor, it's the 1 that's in front there. So if we differentiate 1, again we get a 0. So this is also 0. So this component is indeed 0. And then you can do the same for the remaining components. So the components that you need to check are theta theta, phi phi, theta phi, and then the metric is symmetric, so you don't really need to check the phi theta component separately. So I'm going to leave that as an exercise to check the other components, but as you can see, this component works as well. So that's actually hints us a little bit towards a general statement, and that's if the metric components do not depend on some of the on one of the coordinates. So let's call that on YA for some fixed A. Then dA is a killing vector, meaning that it generates a symmetry. This is not the only expression for a killing vector that you can have. As I said, on the sphere, you have more complicated killing vectors that are combinations of d phi and d theta. But in particular, if it is true, then that the metric components don't depend on a coordinate, then the corresponding coordinate basis vector is a killing field. So I mean, we can check this explicitly. So if we take the derivative, the lead derivative in that direction of the metric, and then take some arbitrary components here, BC, then this will be equal to dA GBC plus GAC dB, 1 with 1 being the one coming in front of the A here, plus GBA DC1. So as you saw before, these are zeros. So this is 0, this is 0, and assuming that this metric component does not depend on YA, we get a 0 when we differentiate with respect to YA. So this is indeed equal to 0. Any questions on that? If not, let's move on. Now we're actually where I hoped to leave off yesterday. We're going to discuss a little bit more about these killing vectors and symmetries, and then we'll jump to integration. So in the first part of the course, you discussed with Julia something that's called Noether's theorem, right? So if you have a symmetry that corresponds to some conserved quantity, now that's a direct analog here when we talk about general general spaces or manifolds, that when you have a symmetry with a corresponding killing field, let's look at what that implies for the geodesics on this space. So killing fields and geodesics. And we'll find, of course, that's why I mentioned Noether's theorem, we'll find that if you have a killing field, then that corresponds to some conserved quantity for geodesic. So consider now that, assume we have a killing field. Field, let's call it K. So this also, of course, pre-assumes that we have some metric here as well. And the geodesic, let me call it gamma. So this means that the tangent vector of this geodesic satisfies the geodesic equation. So this means that that this is true, that the affine connection acting on gamma in the direction of gamma is equal to 0. That's the geodesic equation. So then I can construct the following. We construct the quantity Q, and that's the inner product between the killing field and the geodesic tangent. And as you can imagine, this will turn out to be what is the conserved quantity. So let's just check what happens when we differentiate Q with respect to the curve parameter here. So this is, if we write it out, this is DDS GK gamma dot, right? But this thing here is a scalar. So acting on it with this DDS is the same thing as, yes, sorry. G here is the metric tensor. Yeah. So it takes two arguments, two vectors, and maps them to a number. Okay, so we take this, which is a scalar then, because we take two vectors, we map them to a number. And along this, so along the geodesic, we can write DDS as just the affine connection in the geodesic direction acting on this scalar. Okay, but now from the way we defined the affine connection now before, we said that we should have the product rule. This means that when I have this connection acting on this product of scalars, product of tensors, we have a two tensor and we have two vectors. This should be the same as summing when this differential operator acts on each of them individually, right? So we can write that down. So I have one term where I act on the metric, and I get a new two tensor back that takes K and gamma dot as its arguments. I have another term when the derivative acts on the killing field. So I have that term, gamma dot, and finally I have one term where the derivative acts on the second argument. Okay, so if we just look at these, well, let's start by the last one. So this term. What is here is just what was there, right? So that term is going to be equal to 0 just by virtue of the assumption that gamma is a geodesic. Because just using the geodesic equations for that argument, we get a 0. If we look at the first term, we have a derivative of the metric tensor here. So this depends a little bit on what type of connection we have. But in general, if we assume that that the derivative of the metric tensor is equal to 0, then we say then the connection is called metric compatible. And what this means in essence is that when you parallel transport anything along a curve, then the inner products and so on are going to be preserved. In particular, this is the case for the Levi-Civita connection that I wrote a small note on that on Canvas, that there may be many different connections given a particular space, but there is only a single unique connection which is metric compatible, i.e. fulfills this, and symmetric, so that the connection coefficients are symmetric. And that is called the Levi-Civita connection. So if we have such a connection, then that term is also going to disappear. And we are left with only G of the action on the killing field here. Now for the Levi-Civita connection, and you can check this. So the full computation is in the lecture notes. I'm not going to go through it in detail here, but you can check the lecture notes. But we will have a result which is the following: that if you take the following expression and you switch the order of the indices, then this is going to be equal to the Lie derivative, Lk acting on G AB. So this is true for any vector field, but in particular, if we assume that we have a killing field, then by definition this Lie derivative was 0. Okay, so having a killing field is equivalent to this expression being equal to 0. And this is an expression with two lower indices, so it's a 0-2 tensor, and so it takes two arguments. If I put gamma dot, so the tangent vector, in both arguments, this means that I get 2, because now it's symmetric, gamma dot k of gamma. So this would be a one form, right? Actually, let me do this. Yeah, let me write it out instead. So what this means, let me write it like this: 2 kb, then gamma dot a, gamma dot b, essentially, right? Equal to 0. And this, you can convince yourself, well, it's 2, and then I can put the gamma dot there, and then essentially what I have is, let me write it out incomplete. So it's essentially this, right? It has to do with lowering and raising the indexes using the metric, but what I get is this, equal to 0. And that's exactly the term that we have left, apart from the multiplication by 2, of course. But the multiplication of 2, I can just divide out the 2 and I still have 0. So indeed, if I have a killing field, then this expression is equal to 0. And that just means that the derivative of Q along this quantity along the geodesic is 0, which means that Q is conserved along along the geodesic. So Q is conserved along the geodesic. And this is something that you can use. So next time I'm going to look a little bit at how to use this math in Lagrangian mechanics, and we'll see that this is going to exactly correspond to Noether's theorem. This conserved Q is going to be exactly the conserved quantity that we have in Noether's theorem. But you can also use this in general relativity, for example. In fact, when I give the GR course, which I have not done for a couple of years now, this is one of the most useful relations that appear, because computing things with conserved quantities becomes so much easier than actually solving the geodesic equations. So it can actually be used to draw a lot of physical conclusions about different systems. Any questions? Okay. So I want to go on now. So we've discussed symmetries, and we have discussed derivatives in general spaces. So what's left to discuss, if we want to discuss essentially the calculus on general spaces, is to discuss integration. And so let's start with that. Now, the first thing I want you to note, we discussed it a little bit yesterday, but is that we can't really add vectors or tensors from different points in a general space, because they simply belong to different vector spaces, right? The only thing I will be able to add together are scalars, because they don't depend on the point where you are. Or rather, you can add them without changing bases and stuff like that. But so the only type of integral that we will be able to write down are integrals that result in a scalar quantity. So I want to take a little bit of time to look back now, and this is probably what we'll have time for before the break, on what kind of integrals of integrations are we familiar with in R3. So typical three-dimensional Euclidean space. So you have come across a lot of different integrals in physics. Some of them are integrals over volume. So we have volume integration. And typically what you have then is some volume element dv. So you have some small volume element dv that is spanned by your coordinates, essentially. So you have some coordinate vectors that span a small volume dv, and dv is then expressed. So if these are the so this is the x, if we call the coordinates 1 to y1 to 3, this is the x, the y1, the x, the y2, this should be partial derivatives, and the x, the y3. The volume of this dv if we span it by small changes in each of the coordinates, then dv is equal to dx dy1, the triple product here, dx dy2 cross dx dy3, and then the differentials dy1, dy2, dy3. So this triple product, you know that it describes the volume spanned by these vectors, and then just multiply by the side lengths. So these are, by definition, the E1, E2, E3 that we have been talking about. E1, E2, E3. And what I want you to focus on here is the fact that whatever is in front of these differentials, that is triple product, is completely antisymmetric, right? This triple product. If I change the position of E1 and E2, I get the minus sign. If I change the position of E2 and E3, I get the minus sign. And the same thing if I change E3 and E1. There are minus signs, so this is alternating depending on how I write them. Okay, so these are the coordinate differentials. And then you have something completely antisymmetric. In front. So apart from volume integration, what other integrations can you do? Well, you can integrate on surfaces. So we can have surface integrals. And then you need a surface element. So if you have some surface, let me draw it in some other color. We have some surface here. If we take any point on this surface and we take a small surface element here, it has some normal vector, and it has some unit vectors in the surface to which this normal vector is orthogonal. So these would now be, if I use s and t as coordinates on the surface, this would be dx ds, and this would be dx dt. Then the directed surface element is the area here of this small parallelogram in the direction of the surface normal. So then we write the surface element as ds, and I'm just going to call these vectors now. I'm going to call this es and et respectively. Then this ds is et cross es dt ds. And again, what we see here is that we have some coordinate differentials and then we have something completely antisymmetric. Right? And finally, we can do line integrals. And that's just taking a curve and integrating along that curve. You have a tangent vector to the curve, which is dx dt, where t is the curve parameter. Let me call that et again. If you write that down, then the element dx, that's equal to et dt, right? So this is also something which is a coordinate differential, and then there's something that's, well, completely antisymmetric. I mean, this doesn't say much because there's nothing to commute it with, but in the sense that anything that we can commute it with gives a minus sign. We can't commute it with anything, so by definition, then it's completely antisymmetric. But we see the same structure in all of them, right? In all of them, we have the coordinate differentials, and then something completely antisymmetric in these basis vectors, right? So this kind of gives us an idea about the kind of objects that we will be able to integrate. We want to have something that's completely antisymmetric in a bunch of tangent vectors and maps to a scalar. Well, in this case, we map to a vector, but in order to get something that we can actually integrate on a general manifold, where we can't add vectors from different tangent spaces, we would have to take the inner product of this ds with some vector field. So typically here, what we would do here would be to take some current, for example. So this would be a flux integral of the vector field J through this surface, right? And then this would be scalar. So J scalar ds, we would multiply by J here, and we would get something that is completely antisymmetric in ET and ES. And the same thing here. I mean, we have the X, but we can multiply in this J and we get the scalar, right? So what we want to integrate in order to get the scalar result is something that's completely antisymmetric in these tangent vectors and returns a scalar. So when we integrate something over a three-dimensional volume, we take three tangent vectors as the argument. When we integrate something over two-dimensional volume surface, we take something which takes two tangent vectors as input. And when we integrate over a line, a one-dimensional space, we take one vector as the arguments. Okay? So this kind of tells us that the interesting objects for integration over p-dimensional regions take p tangent vectors and map them linearly, because you can see that all of this here, this is a linear thing, this is a linear thing, this is a linear thing. So we map them linearly to real numbers. So if we want to, and it's antisymmetric, fully antisymmetric. Right? So it's some map omega that takes oh, okay, so P is not a good idea for the point. Let's use Q, that takes P tangent vectors and map them to a real number alternatingly. So alternatingly meaning that if you switch two of the arguments, you get a minus sign. So this, and being linear, means that it's a 0p tensor. So it's a fully antisymmetric 0p tensor. Right? Because it takes p vectors and maps them to a number alternatingly, right? And this is such an important subset of the 0p tensors that it has name. These are called p-forms. And just to take an example here before we take the break, all dual vectors are one forms, because as we saw here with a one-dimensional thing, you just take one argument. It's difficult not to be anti-symmetric when you just have one argument, so any kind of dual vectors maps a single tangent vector to a number, and does so alternatingly, because you cannot alternate between the arguments. So all dual vectors are one forms. If I look in R2, so with coordinates x and y, then all two forms are on the form omega equal to some function of the coordinates, and then the x tensor dy minus dy tensor dx. You can't, for example, have any dx term, because that's not going to lead to an alternating form. So this is just a scalar function, and then you have something like that. So indeed, the space of two forms here on R2 is a one-dimensional vector space. It's a subspace of 0 to tensors. Hopefully we have now convinced ourselves that p-forms are going to be important for integration, right? And you've kind of seen what p-forms or what one-forms are, and you've seen these two forms of R2. So let's formalize here a little bit. Let's write down a more general formulation of p-forms. So in order to do that, I'm going to introduce what is called the wedge product. So given p one forms, I'm going to call them omega I, where I runs from 1 to p, so essentially dual vectors. We define the wedge product of those, so omega 1, wedge omega 2, wedge so on and so forth, until omega p. This is the sum over all elements of the symmetric group of p elements, so permutations of p elements. You remember them from our discussion on group theory. We take the sine function of sigma, I'll discuss that in 2 seconds, and then we take the tensor product of all of these forms, but with the order given by this permutation up to omega sigma of p, right? So this is a 0p tensor. This signum function, it's equal to 1 if sigma is an even permutation, and it's minus 1 if sigma is an odd permutation. So just to mention a little bit about that, in general sigma, so SP can be generated by elements essentially 1, 2, 1, 3, and so on up to 1p. So these are p minus 1 generators, and we say that a permutation is even if it's a product of an even number of generators, and odd otherwise. So if it's a product of an odd number of generators. So this is actually a homomorphism from SP to 1 minus 1, which is a group under multiplication. So this function is 1 or minus 1, depending on if I have an even or an odd permutation. This here is going to be a p-form because the sign function here makes it alternating. If I change position here between 2, I get that I have that in a different element of the permutation group, and I get a minus sign because they differ by 1 permutation. Okay, so this is the wedge product, but since we now know, since dy I, let's write it dy1 tensor dy I2 tensor and so on up to dy IP. That's a basis of 0p tensors. Then we know that if we take the wedge product instead, so di1 wedge, dy I2 wedge, and so on, dy IP is a basis of p-forms. Now, not all of these are going to contribute. Some of them are going to be 0, others are going to be linearly dependent on others. But if you take them all, you will have a basis. You can reduce that basis to a particular number. So how many do we need of them? Well, so what is the dimension of the set of p-forms? Well, in n dimensions, so if we are describing a space for which we need n coordinates, let's note the following. No index can be repeated. Sorry, not in that. In this thing, no index can be repeated, or because of the alternating property, it must be 0. So we can't repeat any of the indices. But also, we can't have that the indices cannot be so the indices cannot be a permutation of the indices of a different basis element. So what that means is that, for example, if I take dy1 wedge dy2, because of the alternating property, this would be minus dy2 wedge dy1. So when I write down the basis for, in this case, 2 forms, I only need one of them. I don't need that one, for example. I can just use the first one. So this means that we can pick p distinct numbers in the set 1 to n, unordered. and then put them into these wedge products. And then we will have a basis for our p-forms. So there are, so if we call the number of dimensions of the p-forms np, there are a number of n over p different ways of doing that. That's choosing p elements out of n in an unordered way. And that's, so you're probably familiar with, n factorial divided by p factorial times n minus p factorial. So let's just exemplify that. If we look at the p-forms in R3, so, and I'm going to use regular coordinates now, so coordinates x, y, and z. So there are actually zero forms. That would be a map from zero vectors to real numbers. That's just a function. This is just a function. And then, of course, there are no. The basis is just the constant 1. The basis is just the constant 1. So this is one-dimensional. Right? For one forms, you should have, so n1, if n is equal to 3, then we have 3 factorial divided by 1 factorial times 2 factorial. 1 factorial is 1, so this is 3, right? And we can choose them to just be the coordinate basis. So dx, dy, and dz. So this is 3-dimensional. The set of one forms in 3 dimensions. And in general, of course, the set of one forms will have the same number of dimensions as the underlying space itself, because one forms is just dual vectors. Right? If we look at the two forms, we have n2, that's 3 factorial divided by 2 factorial, 1 factorial, that's again 3. And the set I can take here is I need to choose 2 out of the 3 indices. And then I just can write them down in any order that I wish. So if I choose x and y, I have an element which is dx wedge dy. If I choose y and z, I can have an element dy wedge dz. If I choose x and z, then I have an element dz wedge dx. Of course, I could also write the x wedge dz. That would just be minus this one. But I write this in this way because it turns out to be nicer later on. So this is again a 3-dimensional vector space. The set of 2 forms in 3 dimensions. And finally, the 3 forms, n3, that's 3 factorial divided by 3 factorial multiplied by 0 factorial, that's 1. So there is only one basis element, and that's selecting 3 out of 3 elements. That's x, y, z. So dx, dy, dz. So this is 1-dimensional. If we go to higher dimensions, we will of course get 0, because there is no way that we can write down a wedge product of more than 3 elements that are independent, so to say. We will always have an index repeated, and so there are no 4 forms in 3 dimensions, or 5 forms for that matter. Any questions? Yeah, so okay, so the question is, how did I generate these spaces? So that's what I tried to discuss here, right? So the way I can pick independent, so in general, my basis is my basis elements would be these, right? And the question is how many of them are independent. So the discussion is that I cannot repeat any indices because it will be 0. Because, for example, dx wedge dx would be 0. So I will not have that here in this one. Furthermore, I cannot have, if I have the same coordinates differentials and I just permute them, then I will get something that's linearly dependent. So that's not a that's not a new independent basis element, right? So the thing to do here is I just pick p distinct coordinates, and I have to use all of the distinct choices that I can. So in 3 dimensions, where I have coordinates x, y, z, there are 3 ways of choosing 2 of them. It's essentially deselecting one of them. So in the first here, I deselect z, and then I can write them down in any order I want, because it's going to be linearly dependent. So for example here, I could have chosen dy wedge dx instead. But that's just equal to minus dx dy. So they are not independent. I can choose whichever of them as the representative. Yeah. And the same thing, of course, for the other ones. And then for the 3 forms, of course, I have to choose all of them in order to get 3. So there's only one way I can do that. And then I can write them in any order I want. It will differ at most by a sign. Okay. So let's do that. So let's just talk about a couple of definitions here now. Or it's not really a definition. It's more of a result of p forms. So this is just kind of conventional now. What we call the component of a p form. When we refer to the component of a p form, we're still going to refer to the component as we discussed the 0p tensor. So a general 0p tensor, you would write it as omega a1 up to ap dya1 tensor up to dyap, right? Now if I, instead of these guys with the normal tensor product, I want to use the wedge product. Well, first of all, if I have a p form, then this thing is going to be antisymmetric. But if I instead want to use the wedge product here, well, I should note that the wedge product contains p factorial terms here, because the order of this group is p factorial. So if I want to write this instead, so for a p form, if I want to write it instead in terms of the wedged basis, then I would have to do that, and I would have to divide by p factorial, and then I would put the wedge basis. And this is because this wedge basis, it contains p factorial elements like this. And then I'm summing with the components here. So that gives p factorial times too much unless you normalize with that. So this can be, because if you look into the literature, you would find this 1 over p factorial appearing, and then you might wonder where it comes from. And it's then good to know that it comes from this wedge product containing p factorial terms. So for example, just to make this clear, for a 2 form, I could write the 2 form omega, which could be dx tensor dy minus dy tensor dx, right? So this has omega 1, 2 equal to minus omega 2, 1 equal to 1, right? So the components. So if I write it down now using this kind of expression, we'll see that it makes sense. So omega, using that expression, would be 1 over 2 because 2 factorial is 2. Omega AB dya wedge dyb, right? And then I can perform the sum over A and B. The terms when A is equal to B will disappear, simply because this is antisymmetric. So I will have 1 over 2, and then I have a term when A is 1 and B is 2. So I would have omega 1, 2. The y1 is x, and y2 is y. Plus omega 2, 1, the y wedge dx, right? Now this is equal to, if I insert the, this was 1, this was minus 1, so I have 1/2, and then I have dx wedge dy minus dy wedge dx. I can use the antisymmetry property for this one now to find out that this is 2 dx wedge dy divided by 2, so just dx wedge dy, which happens to be just what this is, right? And you can see that we had 2 terms in this wedge product, this one, and that's why we needed to divide here by 1/2 in order to get the normalization correctly. Okay, there is another interesting property here. We've been discussing derivatives, and there is a particular derivative of p-forms, which is called the exterior derivative. And it's a derivative map from p-forms to p+1 form. From p-forms to p+1 forms. And we define it as follows. So if we have a p-form omega, then we define d omega as 1 over p factorial coming from what we just discussed. And then we act with a partial derivative, dA1 omega A2 all the way up to a p+1, and then we multiply all of the dy's, dy1 up to dy a p+1. So this is a p+1 form, and it's a derivative map. So you might ask yourselves, is this actually tensor now? Because I'm using here a normal partial derivative. And the thing is, if I would be to change that for the connection, for the covariant derivative, nothing will change, because assuming the Levi-Civita connection is symmetry in the connection coefficients, will make all of the terms containing the connection coefficients just disappear. So it's still going to be fine. So why is this interesting, you might wonder? Well, let's take some examples where we use this exterior derivative. So examples in 3-dimensional Euclidean space. of a derivative of a p form. So let's start by p equal to 0. So this was just functions, right? And we want to differentiate functions. So we have a function which we might call phi. That's a 0 form. Then d phi, according to this definition, that's just dA phi dya. And this you recognize now. This is just a differential that we have been discussing before. So it's comparable to a gradient. Luckily, of course, it becomes the differential, so this notation d phi doesn't really interfere with any notation that we've introduced so far. The exterior derivative, so the differential of a function is just a particular case of this exterior derivative. Let's look at p equal to 1. Then we know that we have a 1 form, omega. And we can write that in the following way. I can write it as omega 1 dx plus omega 2 dy plus omega 3 dz, right? That's fine. This is a general 1 form. If I apply the exterior derivative to this, what do I get? So let's do that. D omega. Okay. So in essence, what I want to do is for each term, I want to apply the derivative in all directions, and I want to wedge in the corresponding coordinate differential. Okay. So for this one, for the first term, you see that if I wedge in the x with this one, I'm going to get 0. Okay. So that's not going to give anything. So the interesting derivatives is and I'm going to use 1 for x, 2 for y, and then 3 for z, and so on. So this means that I'm going to have two interesting derivatives here. It's d2 omega 1, and then I get the y wedge dx plus, or rather, yeah, let's take plus. Plus, when I take the 3 omega 1, I wedge in the z. And I do this for all terms, right? So in the second case, the non-interesting one is the derivative with respect to y, because the y wedge dy is 0. So I have the 1 omega 2 dx wedge dy plus the 3 omega 2 dz wedge dy, and then finally the 1 omega 3 dx wedge dz plus the 2 omega 3 dy wedge dz, right? So let's collect terms with the corresponding bases, right? So let me first take the dx dy. We also have a dy dx here, but that comes with a minus sign. So it's dx dy is minus dx dy. So if I write that down, I have the d1 omega 2 minus d2 omega 1 dx wedge dy. And I do the same for the other terms. So let's take the, what do we take? Let's take, actually, let me move this down a bit. Let me keep that. And let me first take the dy dz terms. So we have two dy dz terms. It's this one, which comes with a minus sign, and it's this one, which is already on that form. So we would have d2 omega 3 minus d3 omega 2 dy wedge dz. and then I take the z dx terms. So I have this one, and I have this one. One of them comes with a minus sign. So I have d3 omega 1 minus d1 omega 3 the z wedge dx. And then finally, I have this term that I already put here. Now you'll notice something, right? So we had a three-dimensional set of two forms, right? And the components I got here, you might recognize them. They are the components of the curl of a vector field with components omega 1, omega 2, omega 3. Where the y dz here would correspond to the basis vector e1, so the missing coordinate. The z wedge dx would correspond to the basis vector 2. The missing coordinate here is 2. And same thing for that one. The missing coordinate is z. And we have the third component of the curve. So the exterior derivative of a one form essentially corresponds to the curve. Let's continue. Let's take p equal 2. So we have a 2 form. And let's go now by the same kind of idea. So we let omega now be omega 1 the y wedge dz, if that's going to correspond to the one direction, plus omega 2 the z dx plus omega 3 what's left, the x dy, right? Now there is only one derivative that I can act here and wedge in the corresponding coordinates in each of the terms. So for the first term here, if I wedge in anything but the x, it's going to be 0, because I already have a dy and dz. So if I take the omega now, the only thing for the first term that's left is d1 omega 1 the x wedge dy wedge dz. The same thing for the second and third term. It's d2 omega 2 dz wedge dx wedge dy. And finally, d3 omega 3 dz wedge dx wedge dy. Now, all of these are even permutations of x, y, z. So I can exchange this for x, y, z and this for x, y, z. They're all the same. That means when I collect terms here, I get d1 omega 1 plus d2 omega 2 plus d3 omega 3 dx wedge dy wedge dz. This is also something you recognize. This looks an awful lot like the divergence, right? So it's kind of tantalizing to just see that, and we'll see how that plays out in a little while. Finally, for p equal to 3, well, then omega is equal to whatever function you have. It's called omega 0 dx wedge dy wedge dz. There is nothing that you can wedge in here without getting 0, so the omega would just be equal to 0. There are no 4 forms in 3 dimensions. Just a short remark. Note the following, that if you take the exterior derivative of an exterior derivative, you get 0. And why is that? Well, essentially, if you do that twice, right? So this would be, let's just write it out. It's 1 over p factorial, and then you have dA dB omega c1 up to cp dya wedge dyb wedge dyc1 up to dycp, right? But this is antisymmetric when you exchange A and B, and we are assuming that these commute, these partial derivatives, which means that it's symmetric. So this is indeed equal to 0. Now this corresponds to taking the divergence of a curl, for example, being equal to 0. Or if you take the differential of such a differential, that's the curl of a gradient, which is also 0. It's the same thing. Okay, so finally, the last 10 minutes, we come to actually performing integrations in our general spaces. So integration. Now we're going to define the integration over some p-dimensional subspace. So we consider a p-dimensional subspace omega parametrized by p parameters and I'm going to call them Ti, where I runs from 1 to p. Okay, and that parameterization is some function then from omega t, the subset of Rp, where the coordinates live, to omega. And then we can define the coordinate lines gamma I. Those are the lines where you keep all coordinates except for Ti fixed. So all coordinates except Ti are fixed. And those are curves, right? Any coordinate line is a curve because when you change that coordinate, you get the curve. And so a curve has a tangent vector. And as usual, we just denote those with a dot, comparison to the curves themselves. Now at any point, this set gamma dot I span a non-degenerate parallelogram, right? Because otherwise I would have degenerate coordinates. Okay, so then we can ask ourselves, what is the volume of such a parallelogram? Well, if we have a volume form, so a P form, we can define it using a P form, which I'm going to call omega. And we say that the volume element here, the p-dimensional volume element, that's just omega gamma 1 dot, gamma 2 dot, up to gamma p dot, dt1, dt2, and so on, up to dt3. And now we have exactly the same structure as what we began with, right? When we were discussing here in the beginning, when we started talking here, we were discussing these things. The volume integral. We had, well, some 3 form mapping 3 vectors to a number times the coordinate differentials. Some number times the coordinate differential, some alternating function of the vectors times the coordinate differential. Well, once you multiply in the j. And the same thing there. So indeed, this is the kind of thing that we want to integrate. And now we can just do that because in RP, we know how to integrate over this region. It's just your usual multivariable calculus integral. So we define the integral of this P form omega over the region capital omega. We define that as the regular multidimensional integral of this thing. So omega taking all of these tangent vectors and then all of the coordinate differentials. So this is the definition of the integral of a P form. So you can integrate the P form over a P-dimensional subspace. So for example, if you want to integrate over a volume, for example, then you need to have a volume form which has the same dimension as the space itself. If you want to integrate over a surface, a two-dimensional surface, then you need to integrate the two form. So we have 4 minutes left. Let me just take an example here of such an integral, and you'll see that it comes back to something that we are familiar with. So let's take a surface integral in R2. Sorry, in R3. So this is kind of a flux integral that we would like to make. And omega here now, it's a surface parametrized by S and T. Okay? Okay. Then we need a two form, because otherwise we can't integrate over this. I don't have access to any kind of canonical two forms, but I do have access to a canonical volume form. So the canonical volume form in R3 in Cartesian coordinates is just, I will call it epsilon. It's the x wedge dy wedge dz, because the volume of the unit cube is 1. Okay, so that's a 3 form. So how can I use a 3 form to get a 2 form? Well, I need to insert something into it. I need to insert a vector into it. So we define the insertion of a field I into epsilon. This is supposed to be a 2 tensor. So x, y being vector fields, it should be a number. I define that as epsilon, and we now insert j into the first argument, and then x and y. Okay. So what does this mean for our integral that we can construct? Well, the integral that we can construct of this 2 form now over this 2-dimensional surface, so I j epsilon over omega. If we look at the definition now, well, the definition tells us that we should insert j into the first. So first of all, we should have epsilon I j k, which are the permutation symbol, which are the indices, which are the components of this tensor. Then in the first argument we put ji. In the second argument we should put the first tangent vector. So that's the xj ds. Then we put the xk dt, the second coordinate, ds dt, right? But you recognize this. This thing, again, we are integrating here over the region of S and T parameterizing the surface. But you recognize this. This thing here is nothing else but the triple product of stuff, right? So it's going to be J scalar product ES cross ET ds dt, still the integral over omega t. And this now you recognize as a surface element. We discussed it in the beginning when we started discussing these integrations. So indeed, this is just the flux integral of J through the surface omega. So I hope that this convinces you somehow at least that this kind of construction makes sense and is going to be useful in generalizing all kinds of different integrals here. Okay, it's 12 o'clock, so I'm going to stop there unless there are questions. IJs. Okay, so this here is just a map from it's the so-called it's the insertion map from so it maps a P form to a P-1 form by inserting essentially the vector field that you have in the index into that form. So this is what I'm doing here. So I'm inserting J into the first argument of epsilon. And assuming, of course, that I have J fixed, then this is a 2 form because it takes X and Y, 2 vectors as arguments, and it's alternating. And so I can integrate that over a 2-dimensional surface.